Alright, so hello everyone. My name is Michael Valdron. I am a master's candidate at Ontario Tech University, previously known as UIT, up in Ontario, Canada. This is my second publication at IEEE IRI with my supervisor, Dr. Ken Poo. So I'm glad to be back, even though not physically, to present what is essentially a summary of my thesis research. So without further ado, I present our research paper for this year's proceedings, Data-Driven Relational Constraint Programming. So to begin, let us look at an overview of problems which can be implemented using constraint programming. For those who are unfamiliar with constraint programming, this is a form of programming for modeling some discrete optimization problems. As we can see here, some problems include planning and scheduling, routing, software verification, model checking, and equivalence checking problems. Along with constraint programming, we have databases. There have been tremendous advances within databases, and databases have been increasing in size recently. With large databases, there poses a few issues when trying to perform data-driven decision-making. Ensuring equality and safety with data becomes an issue, as integrity checking may not be enough when the data we are dealing with increases and the decision-making problems become more complex. With integrity checking, the complexity is typically in polynomial space, but with issues such as satisfying other constraints or performing optimization are typically in the NP-complete space of complexity. For SAT solvers, these kinds of NP-complete problems are perfectly suitable for them. The problem is that very little work is done to incorporate SAT solvers into the data pipeline environment. So, with the motivation to contribute a solution towards this, we present the following material. The first stage of our idea is to embed constraint programming within the relational data model to allow for the perks of SAT solvers to be taken advantage of within relational database systems. This involves extending the relational data model to include constraint programming members as types within relations and views. Also, the extension of SQL to include constraint relational algebra, as I go into in a bit here. So constraint relational algebra involves the extension of types to include both constraint types and literal types from constraint programming. This also gives the ability to create aggregation queries against constraint relations, and then solving constraint relations as we do in constraint models. So here we have an example of a theoretical relation which would be in a database that supports constraint relational algebra. So over here we have a column with a traditional int type and int values. And in these two columns are typed as var ints with unknown values. And these represent integer variables from constraint programming that would need solving. Here we see an example of creating constraints in a view of a relation. The query that creates the view creates a new column with the type constraint, with constraints in them. And these constraints are generated using extension operators that are similar to the traditional ones from SQL. In our literature, we denote these extension operators to be surrounded by colons, as seen in the query example up here, 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 and here. Aggregation can also be done with relational constraints. This example here shows the creation of a view that includes a single constraint which ensures that the sum of this y column is less than the value of 1,000. We can also see that we can perform traditional aggregation alongside constraint aggregation in the form of creating a row count here. Here we propose an additional query type which creates a goal. Goals will add constraint groups to the underlying constraint model for later solving. We simply create goals by using a traditional SQL query which defines the constraints, either at runtime by defining it right within the select query, or by selecting a pre-existing constraint from a relation or view. And now we can solve the constraint relation here by selecting our variables from the constraint relation and then invoking this solution operation on our constraint relation, and then this would produce a view of the tabular integer values for x and y. So sounds great so far, but there's still lots to be done here. One feature needed is the ability to iteratively and interactively debug relational constraints. This is important when we run into infeasibility within our constraint programming model. Therefore, our second stage of work, we propose operators for supporting such a feature. So now let's look in the motivation. Suppose we have a relational constraint program of constraints and literals. This program could be infeasible for a number of reasons, which include an error or errors within the queries, inherent conflicts in the data, or unreasonable expectations of the constraints. To combat these problems of infeasibility, we provide the following debugging capabilities: localization of conflicting constraints, and a method of generating partial repair solutions. So we have two definitions to go over and two proposed algorithms to look at. So let's start with conflict sets. So a conflict set in our work is defined as a subset of conflicting constraints which belong to a CNF where the subset of constraints or constraint enforcing upon the literals is infeasible. A type of conflict set that we are interested in is called a min-conflict set. This is a conflict set which none of its subsets are conflict sets. The illustration below shows that we have this set over here, which is obviously a conflict set due to its conflicting constraints. And then over here we have its subsets. And as we can see here, that if we were to run these subsets individually against the literals in the model, they are feasible. They would produce feasible solutions. So these are not conflict sets, which means that this conflict set over here, the superset, is a min-conflict set. So for our first algorithm, con, we will take a CNF as input and then produce a min-conflict set as a result. This algorithm has two implementations called bottom-up and top-down, which we will have a brief look at. Here we have the bottom-up approach for con. It searches up the power set for the first min-conflict set and then returns it. Here we have the top-down approach of con, and this implementation does the opposite of bottom-up by finding the first min-conflict set starting with the full CNF and then working downwards. Full details on this algorithm and its implementations can be found in the paper. So now we go into repair sets. So a repair set is defined as a subset of constraints within a CNF which removed from the CNF is feasible. So if the difference of the CNF and the subset combined with the literals is feasible, then we have a repair set. Similarly to min conflict sets, a min repair set is a repair set with no repair set subsets. Finding a min repair set is to ensure that we change as little as possible when repairing the CNF. So our second algorithm takes a CNF as input and then results in a min repair set as a result. So how does this algorithm work? Well, it turns out that we can perform the max-sat optimization problem to produce a min repair set. This is done by having an objective function seen down here, which is of the max-sat model. So here we see the full algorithm. And the important part to note of it is that it returns, after solving the max-sat problem, the indices of the unsatisfied constraints which give our min repair set. For more details on the full algorithm, can be seen in the paper. So now let's briefly discuss our implementation. So our source code was written in the Clojure programming language, and our choice of SAT solver is Google OR Tools CP SAT solver. So the Clojure language, for those who do not know, is a Lisp dialect language with high-level functional programming in mind. It was created by Rich Hickey back in 2007, so a fairly recent language, and it was built on top of Java. Google OR Tools is a suite of optimization tools for solving some of the toughest problems. Originally developed and currently maintained by Lauren Parent and Vincent Vernon at Google, OR Tools is now open source and accepts contributions from the community. And it includes the CP SAT solver, which we use, and also includes many other types of solvers for problems such as MIP integer programming and linear programming. Since OR Tools has a release in Java, we can actually import the library right into Clojure. And we've created our own APIs, which we can see in these screenshots, which makes utilizing the Java APIs much more, as we call it, Clojure-esque. So to go over our experimentation, so our first experiment is the 3CNF problem. This problem defines a random 3CNF with disjunctive clauses. Each of these clauses contains literals of variables and their negations, as seen in the figure below here. And the solution for these literals is feasible if all of these clauses are satisfied. And as we add more clauses to this problem, it becomes more complex. So for our second experimentation, we evaluate the running time of our con algorithm on segment overlapping problem. For this problem, we construct by generating 1D segments with random lengths. Each pair of segments has no overlapping constraints tied to them, and which essentially means they can't overlap. A simple example of this can be seen below, where the top solution, where we have 3 segments here that are not overlapping, is considered a feasible solution, whereas down here, where we have the same 3 segments are overlapping each other, which means it's an infeasible solution. So to go over our experimental results here, the experimental results for the 3CNF showed exponential growth in both the running times, for the running times in both implementations of con here, as clauses were added. And this is not really particularly a surprise to us. For more details, see the paper. And but for our repair algorithm, we noticed that this algorithm ran much faster with a linear growth in running time over a much larger amount of clauses. So this shows that our optimal repair approach can be done with large models. And then for the segment overlapping experimental results on our algorithm con showed an interesting pattern. We mainly see this in the bottom-up results here, where the running time varies at different epochs. So here it spikes up and then it dips down again, and you can see it like jumping up and down here. And this shows that depending on where the min conflict set is, depends on the running time of con. So the bottom-up approach would have the inverse running time as top-down and vice versa. So to summarize, we presented a relational constraint framework which allows for data-driven constraint SAT solving and decision making. Second, we presented operators to perform algorithms which produce results for supporting iterative and interactive constraint debugging, including an efficient repair approach by fetching repair sets from the MaxSat problem. And future work includes static analysis and query optimization of the constraint program, and also visualizations to support the operator results to better reinforce the interactive part of debugging. So that is everything. I thank you so much for listening to our presentation, and I will now take your questions. Thank you.